It was a very good description of my background. So thank you very much. And thank you for inviting me today for this presentation. Can you see my PowerPoint? Well,
Yeah, it's good.
okay. So I'm going to talk about organic soil that we have worked in a project for one of my PhD student completed the project and one master's student work with that. And also currently another PhD student is working. Organic soil is a big challenge in Canada, and especially when we are dealing with different kinds of problematic soil. Organic soil comes into picture all the time because of the special nature of the organic soil. So with my background and this experience with this big project that we work in collaboration with many people, I have a knowledge about the lab scale characterization. We also have done field scale characterization of this soil, and then we have use this MICP techniques to see the behavioral changes of this soil. So that's why I feel like I have a complete picture, and then Professor Reddy will be sharing all those publications related to that. So I have divided the whole presentation into several parts. I believe it's a lot to talk about, and when I was looking into my data, I was thinking, oh my God, I have so many things to share, and I don't know which one I should be focusing more on. But before we start to solve the problem, we need to understand the problem, how deep the problem is, and what knowledge we have from so far from our literature and other researchers work on these areas. So looking into that, I'm going to talk about a little bit on the background, why it is important for Canada especially, and the technology, whoever it develops, and if it is working, anyone can adopt that technology if the boundary conditions are same and the properties are same. Then we will be talking about our lab data, field data, and bringing the MICP and how important was that for us to look into that approach, and why we are whole geotechnical industry is moving towards sustainable solution to fight climate change. We play a significant role as a geotechnical and geoenvironmental engineer for the society. So and then talk about some gaps that we see in MICP so that people can pick up on that and think about what can be done in future. So starting with the background, as I said, that in Canada, organic soil is an issue, and the special type of organic soil that I'm talking about is muskeg soil, because of the energy pipelines that we have in Canada. In many parts of Canada, they are buried in this type of soil. So it covers around 1.5 million kilometer squares, which is around 12% of the Canadian landscape, which is huge. We cannot ignore them. And muskeg soils are distinguished by their high initial void ratio and water content. Classified as one of the problematic soil, it's no need to mention. We know that organic soil is part of that because of their high compressibility and low shear strength. We have to have a better understanding. So thorough understanding and precise estimation of muskeg properties is mandatory for soil pipe interaction design, because I started by saying that pipeline is an issue, and characterization and stabilization of muskeg should be performed so that we have a better understanding. So typically, the chemical stabilization are used for any problematic soil, and the widely used option is cement. And then cement industry produce 8% of the global carbon dioxide emissions. So all those are true. And when we have to think about the climate resilient infrastructure, we have to stay away from those chemical stabilization that produces carbon dioxide emissions. So there are people who are working on different kind of industrial byproducts like bottom ash, fly ash from different sources, rice husk ash, and then lime to stabilize the soils. But then these are not all very sustainable approach, because this produces some sort of PAH, the polyachromatic hydrocarbons in some of this from these materials, and which makes it not very sustainable approach. So what are our options? The option is go to the nature, find a solution which is nature-based solution, and that's why bio-based approach to become getting more popular becoming more popular for a geoenvironmental field. I I know that we are familiar with the MICP technique, but I just wanted to showcase that the schematic diagram that we have developed based on the understanding of the MICP. So what is MICP? It is a biomedical method for soil stabilization with the help of urease active microorganisms, usually bacteria, to produce calcium carbonate. So calcium carbonate provide the strength of the soil when we have a right combination of the media and the bacteria, and that produce the calcium carbonate to provide the strength to the soil. Urea and cementing salt solution like calcium chloride added to the soil along with the urease active microorganisms. So a special type of bacteria which can produce that enzyme that should be added to the soil, and then with the proper media, as I said, that urea and cementing salt like calcium chloride. So we have two phases here, two stages. One is the urea hydrolysis, and another one is calcite precipitation. So the first stage, when we are looking into the urea hydrolysis, in this area where we have ammonia and carbon dioxide by the urea enzyme that produces. And then the calcite precipitation is the calcium ion from added cementing salt that we talked about, the calcium chloride that reacts with this biocarbonate and ion from the calcium carbonate and form the calcium carbonate. And that fills the voids of the soil so that it, creates the crystal deposits, and that leads to the gain of the strength. So this is how the MICP process works. So it's widely used by this bacterial cell, that is finding the right kind of microorganism is important part here. And creating the environment where these microorganisms will be growing and developing those calcium carbonate crystal. These are the important factors. Where we can apply MICP, and in our field, we have been seeing that the most of the applications are related to the improvement of the soil quality, hydromechanical behavior, erosion control, but there are more to it. Rather than stopping our thinking on the certain geotechnical application, we can start looking into the heavy metal adsorption, other kind of applications for biocementation in the concrete or building materials, so that those things can add on to the new knowledge of this field, and then we can have a better solution for the sustainable approach in the construction industry. So what I wanted to showcase here today, develop some new correlation based on our data and the literature, estimate index properties and the compression indices, and looking into the laboratory and the field characterization, identify an undrained shear strength, evaluate the effect of sample disturbance on the compressibility properties of this organic soil, and find out the optimum urease active bioslurry weight, concentration, and cementation cement solution volume. And we also tried that bioslurry with a percentage of sand. So we will be looking into optimum sand weight in the behavior as of the muskeg soil as well. The first item is the correlation. So looking at the correlations, as you can see, lots of data collected from the literature and our own data. And then we have developed relationship of the void ratio. So relationship of the void ratio with respect to the water content, and relationship to the void ratio with respect to the organic content. And then we combine those two parameters. So through 3x, 3D distribution of the data. So organic soil, organic content, water content, and the void ratio, and came up with a new relationship to calculate void ratio. So from here, we saw that the proposed equation for void ratio as a function of the water and organic contents present less scatter than the correlation with the organic content only. That, as you can see from this figure, this one is less scattered data than this one over here. We also have looked into the data for the bulk density. Same way, bulk density with respect to water content, organic content, and a combination of both organic content and the water content. So the bulk density tends to settle around 1 gram per centimeter cube for water content higher than 500% and organic content higher than 50%. With the literature, Denhan and Elmer 1994 equation is a good agreement with the proposed equation for high organic content. Our proposed equation for bulk density as a function of both water content and organic contents present less scattered data with correlation with the organic content or water content only. So this has a less scattered relationship. The next one is the compression index. So we have looked into the compression index again in terms of water content, organic content, and a combination of both. Many points are located outside the lower boundary proposed by McFarland in 1969, but they are located within 95% range. As you can see from this dotted line over here, the black line, this is the outside boundary, but we saw the data fall within the 95% range. And the compression index is best determined based on the water content. So this data set is better to represent the CC value, and the high variation of the compression index at very high organic content over here in this side of the data. It's because of the data we have seen from the literature Dutch peat measurement. So it's a different set of data that we saw. Now we come to laboratory and the field testing with our knowledge from the literature review and developing some new correlation. And we looked into the soil properties in the lab scale and also looked into the data in the field scale. So the site we have collected our soil sample is Bolivar Park, Surrey, British Columbia, Canada. We identified and designed the plan with our industrial partner. And we have looked into several locations where we collected our data at soil at 3 different depths. And we are going to talk about that here. So in this table, it shows the different zone that we have identified at the site. Just I have mentioned it is in Surrey, British Columbia. Zone A is between 2 to 4 meters, and B is between 4 to 5.5 meters. C is between 5.5 to 7 meters. So we have 3 different depths, and we have initial lab testings on index properties with the different properties that are identified, which are important for organic soil. What is the water content, what is ash content, what is organic contents. Then Falcon tests were performed because just looking into the liquid limit data based on Casagendra was not wise for organic soil. You need to double check the data with another approach. So Falcon data was showing similar results with Casagendra method. So it was kind of, justifying the approach having 2 different methods to confirm the parameters. Fiber content, weight and dry density is a specific gravity, degree of humidification, which is important for the organic soil. Then we have compressibility properties, shear strength properties from those tests. We have few important parameters here, the conditions that we applied for consolidation test, the load ranges and the direct shear test, the shearing rate and unconfined compression test, and the sample sizes and the loading range. So what we have seen from this data, as I said, that we have 3 different depths, and then we have identified all those properties, and then we have a little bit of summary over here. So depth A is classified as hemic peat of high ash content, and depth B and C soil are classified as hemic peat of medium ash content based on the percentage of ash we have seen in this soil. Depth A exhibits less water content, organic content, fiber content, and high weight density, and a specific gravity. As depth A is located directly underneath the field's sandy layer, So the percentage of minerals is more than other depths. That's why we have seen that behavior in the depth A soil. Depth B and depth C have almost the same properties except for the water content, and depth C has more water content than depth B. The Falcon method and the Casacento method for the liquid limit test showed similar results, which was important. Then we move on to our compressibility properties. We have looked into the E log prime curve, so the void ratio and applied stress. We have data from all those depths, and we are calling them as undisturbed samples, which is collected on the tubes, and disturbed samples, which is digged into dig from the site. So we have two different sets of data for the same depth. So we have in total of 6 set of data here with respect to void ratio and applied stress. Depth A exhibits less settlement than depth B and C due to the high percentage of minerals, as I just mentioned in the previous slide. Depth C has a larger settlement due to the high initial water content and secondary compression index C alpha, and then primary compression in properties. CC ratio is ranging between 0.06 to 0.08. Both the remolded and the undisturbed samples higher than the ratio proposed by the other researcher previously. So these are the data over here. And then if we have looked into the CC value before and after unload reload cycle, so that's what we have here. We have 2 different sets of data for 3 different zones with a ratio of the compression index after unload reload cycle. So that's also interesting to see how it changes. And then we have shear strength parameters. We have an average angle of internal friction, 31 degrees, and shear strength intercept is 7 kPa. As you can imagine, it's a very small intercept. And now we are looking into undrained shear strength from the field test. This is important because when we are doing the in situ testing and what type of parameters we should be calculating and looking into to calculate the undrained shear strength, which is widely used for organic soil. So the relationship here is undrained shear strength is related to the tip resistance with respect to the parameter NKT. And if you are using the ball penetrometer, then it's related to the ball coefficient N ball. So the value we have seen NKT of 8, usually in average value between 6 to 12 are proposed for the organic soil as comparing to the 15 that we use for fine grained soil. We also have seen in ball value is 9, average between 8.5 to 10.5, proposed for the soil, organic soil, as opposed to 11, which is for the fine grained soil that, Contech, the company that use the data, the field test they typically use for this type of soil. And the ball penetrometer test shows a similar profile of the undrained shear strength in 2 test holes as opposed to the seismic cone penetration test. Ball penetrometer is more suitable for soil with higher water content. That's another kind of observation from this field test data by looking into ball penetrometer test and the seismic cone penetrometer test. We have come to a conclusion that the ball penetrometer is better when you have higher water content. The least accurate laboratory test is the UCS data. It doesn't simulate the real stress state of the soil. The Falcon laboratory test showed a good agreement of the SCPTU data from the field. So by knowing all those characterization, now we will move on to talking about the bioslurry preparation that we have used for MICP techniques. So in MICP, we used the bioslurry approach for organic soil after doing some initial investigation on the approaches available, and then we identified the bioslurry would be the most appropriate one. what we have worked on in the steps are shown in these images here. The process of preparing bioslurry, we are is the growing bacteria that we have used, Spirosaurocina pastorari, in the ATCC on 1376 media. And then we have used the urea and calcium chloride to the bacterial solution and start that for 12 hours at 600 RPM, centrifuging them, the bioslurry mixture for 20 minutes at 4,000 RPM, getting rid of the supernatant, and the bioslurry is settled in the bottom of the centrifuge tube that we saw here. That's the first step of preparation of the bioslurry. Then we have used that bioslurry to the soil, mixing the predetermined soil mass with the appropriate amount of bioslurry by weight. Add the mixture of the soil and the bioslurry to the consolidation ring. Place the consolidation ring between the two 3D printed gaps that we have designed and printed, and I'll be showing that design in the next slide, and tie them together so that we have a proper adjustment of this cell on that 3D printed caps, and then injection of the fast cementation solution that we have the setup over here. So this is the 3D printed caps that we have designed to accommodate the consolidation cell, so that we have a proper arrangement of adding the injection of those media and also allowing consolidation to take place. So this is something that you can see on our publication as well, how to design those and then print it out for the test setup. So let's talk about the results. So what we have worked on the bioslurry approach, we have three phases of data that I wanted to showcase. So first one is the effect of bioslurry concentration that we will be looking into, and then bioslurry by weight, and the effect of cementation level. And then we have used several level of bioslurry concentration. We started with 0.2 mole per liter to up to 1 mole per liter. And these are the the identification of this concentration were done by several trial and error. And then when we saw the changes happening, we put them for the publication and the data, and then the other ones were just for our own record. And we also looked into the microstructure so that we can see the crystal formation in the microstructure of the soil. And that gives us a complete picture of the overall behavior of the soil after using bioslurry approach. So first one here is data for the concentration, effect of bioslurry concentration on the CC and CS, so compression and swelling indices. And then we have three sets of data here. The green one is the swelling data, swelling index data, and then CC, we have two different sets of data. One is before unload reload cycle, that's a blue line, and the orange one is after unload reload cycles. And starting with a 0% treatment, so that means you see this is the high value when we don't have any bioslurry in the organic soil, and then we saw that drops significantly. Then we see the secondary compression index data for effect of bioslurry concentration, and then we have two sets of data. One is 0.4 mole bioslurry and 1 mole bioslurry, and then untreated data on the red line over here. Again, we have data for during the loading stage and then unloading stage, so that we have two sets of data as well for secondary compression index. Then we looked into the stiffness properties. We got the stiffness properties E data on these unload reload parameters, and then the undisturbed soil, untreated soil, the data is on the dotted line over here. and with respect to the changes of the concentration of the bioslurry. And then we have also developed the data for constraint modulus. And as you can see, the untreated sample is the red one, and then the value increased over there with an increase of the concentration of the bioslurry. So two sets of data again over here based on the unload reload cycle and the before unload and then after unloading cycle. So effect of bioslurry concentration and the microstructure. So we saw that XRD patterns, because which is important when you have crystal formation, we have to look at the data on in terms of the microstructure of the soil and identify the chemical present in there. So as you can see from this ACM data, the spikes, crystal spikes on there, indicating the formation of calcite. And if you look into the chemical composition of those untreated sample to 0.4 mole bioslurry treated sample and 1 mole biotreated sample, bioslurry treated sample, you see that increase on this calcite 35% and then 57%, so, which is significant. So that parameter indicates that the formation of the crystal in the microstructure of the soil. Then we look into the phase 2 by the weight of the bioslurry. So same behavior we have same parameters, the similar parameters that we have seen before, we are looking into them again with respect to the different approach of the bioslurry now by weight. And then you can see again the changes happening on after treating the sample with respect to the increase of that weight. So this is the 5%, and then we gradually have up to 20% by weight increase both on the CCCS data and also the secondary compression data. Secondary compression data is important for the organic soil because we see the secondary settlement time dependent settlement is very common in this type of soil. And then we looked into the effect of cementation and the properties of the soil. So now we are looking into effect of cementation with respect to the volume of concentration solution and the volume of pores. So with this ratio, if you just see the started with the 0 when we didn't consider any bioslurry effect, then 1, 2, 3, 4. These parameters are selected based on the literature and previous research in this area. And we also see the impact clearly in both compression and swelling indices and the secondary compression data. And when we have looked into the shear strength parameter, we saw that untreated sample and the treated sample have a significant differences in the values. So starting with when we have a 2 millimeter displacement, we have seen this parameter over here, the angle of internal friction, which is the most important one, then the intercept, the C prime value. So we saw the changes of, it shows the increase of those parameters, which is positive sign on this treatment that we saw on this soil. Now the next one, we are going to talk about the Sand-bioslurry. So we are having this added sand into the design and then talk about that. So let's move on. Okay, so we have two phases here. We are looking into the effect of sand percentage, and we are looking into the concentration level. And then we have reduced the number of tests in this part of the design because we just wanted to see whether impact, if there is an impact of sand adding to the organic soil when we are also adding the bioslurry. So again, we looked into the E-log data, so void ratio and applied stress, effect of sand on this behavior, and you see the red one over here is the untreated sample, and then we saw any percentage of sand, 10%, 15%, and 20%. So there is a change from the untreated sample, but then the changes between those individual percentage of sand is not that significant. And we also looked into the compression and soiling indices. So based on the added sand behavior to that. So this data is kind of interesting. I have a summary to talk about altogether. Then effect of sand percentage and the compressibility properties, CS and then secondary compression. So that we have looked into, again, this is swelling index data, and then effect of sand on the secondary compression in this data. So the red line is over here, untreated sample, and then different percentage of sand added. So you see the reduction of those values. And then a stiffness parameter, we saw the treated samples with sand only, and then we have seen that sand plus 10% bioslurry. So when we have sand plus bioslurry, our stiffness improved. Same thing on the constraint modulus. If you have untreated sample and then we have sand plus bioslurry, those parameters improve. So we are just moving, getting a higher values of those stiffness parameters. And same thing with the microstructural data. We saw the chemical composition. Now the chemical composition, the increase of calcite in the system is lower than compared to what we have seen without sand. So it is interesting to observe that, having sand in the system, it does not have enough calcite produced in the microstructure of the organic soil. And finally, looking into the soiling indices, compression and soiling indices for impact of cementation level. And we have two different data for compression index, as we have been showcasing that before unload and load cycle and after unload and reload cycle, and then we have the soiling. So these two cycles didn't make a huge difference on on the CC data, but then we also have the soiling index data for these properties and shear strength properties, and we saw a little bit of improvement on the internal friction angle. Is not that significant like the previous ones that when we have added bioslurry to the organic soil itself. So if I just summarize the key findings of the work, we have developed new correlation for the muscic soil and organic soil based on the water content and organic contents, which are very significant correlation to be used by the industry. Then we also saw the water content more than 500%. For water content more than 500%, the bulk in density tended to settle around 1 gram per centimeter cube. And we also saw the specific gravity data around 1.5, which I didn't present, but this is what we have observed. A lower limit for compression index, CC, determined as a function of the water content proposed by McFarlane, and which is did not cover many recent data points that we have, and it proposed 95% confidence range data point for based on the data we have plotted, literature and our own data. And the CC after the unload reload cycle was quantified as 0.8 from the interpreted one before the unload reload cycle. NKT, the parameter that is used for the penetration resistance with respect to this parameter and find out the undrained shear strength data from the field test, is 8 for the soil, and we proposed 8, and N-ball is average parameter for N-ball is 9. We found that 0.4 mole per liter bioslurry was the optimum bioslurry concentration. And at 0.4 mole per liter bioslurry concentration, we saw the CC and C alpha, the compression and the secondary compression decreased by 50%. And M value increased by 18%, the stiffness. And then E value increased by 45%. Microstructural analysis justified why no further improvement occurred after 0.4 mole per liter, because we saw there is no changes happening in the microstructural level on the calcite percentage after 0.4. So that's kind of, justified the relationship that we have seen for the compression index data and the stiffness data. And no significant effect is noticed when bioslurry weight and the cementation solution volume increased. And in the mastic soil stabilized with the MICP and sand from a local source, that's another option, because if you have locally available sand and you're using that as a stabilizing factor, that can be useful. But with the 20% sand and 10% bioslurry, we found that that's optimum, and the E value and CC decreased by 70%, and CS decreased by 80%, and C alpha decreased by 60%. And stiffness properties, E and M, increased by 50%. No significant effect is noticed when the cementation solution volume is more than the pore volumes. So those are the findings from our work, if I summarized that way. And then I just want to talk about a little bit on the research gap on MICP. MICP techniques are primarily confined to bacteria, because the research, what we have seen so far, is a certain strain of bacteria that used for MICP. However, many other areas active microorganisms are available, which is some of them are like fungi group and microalgae group. So the focus can be driven into that direction to look into the future area of research in the MICP to further strengthen the knowledge in the biogeotechnology. Bacteria-induced MICP is a non-compatibility with soil of a smaller pore size and has no non-uniform precipitation within the soil matrix, causing strength issues. So this is a research gap that can look into further how to incorporate MICP in a form of composite, not just individually looking into MICP, but develop some biocomposite with the help of other stabilizing materials. MICP with urea results in excessive ammonia production, which is not suitable for environment, especially aquatic plants and animals. So that's another factor to look into. MICP has the potential to be implemented for the capture of greenhouse gases such as methane and carbon dioxide, which can contribute significantly in our fight against climate change. And the life cycle of the byproduct of MICP that not been studied in depth. So looking into the durability, long-term performance, and the effect in environment, all those factors can be studied. We have a list of publication in this project related to some chemical stabilization, and then MICP methods described thoroughly in our Journal of Geotechnical, our publication on the Journal of Geotechnical and Geoenvironmental Engineering and the Canadian Geotechnical Journal, and then other ones are correlations and new approaches, and some review articles on the science of the total environment. And I wanted to acknowledge my collaborators in this big project that we work together with Professor Dharma Vijayavikrama from UBC, Dr. Emmanuel Salifu from Center for Biomedicated and Bioinspired Geotechniques, Arizona State University. My past PhD student, Dr. Almochi, currently working in the industry. Bigul Poker, currently working in the industry, is completed master's. Current PhD student, Akanksha Bhoral, and all the funding agency, NSERC, MIDEX, industry partner, TC Energy, Letcore, Contec, and of course, EBC, which supports us with the lab support system. And stop here and happy to answer any question you have.
Yeah, thank you. Thank you so much, Siddiqua.